Okay, let's, you ready, Ani? Yeah? Let's go ahead and get started. So, just for context, we've actually done a lot of the sort of preliminary work we had to do. We've talked about the manipulator equations. We've talked about feedback linearization. We've introduced sort of nonlinear dynamics. We've talked about optimal control. That's just 4 lectures, right? So, and dynamic programming. So now we start actually looking at more advanced systems. We've been thinking a lot about the double integrator, the pendulum, and we're going to start sort of ratcheting up the complexity a little bit, and looking at some of the model underactuated systems this time. We're actually, you'll see, we'll go back and when it makes sense, we'll go back and we'll look at the way things play out on the pendulum or the double integrator or something, just because that's such a system that those are systems that we can really understand, and we can understand the new algorithms on these old systems, and that's very nice, and see how they compare to our, dynamic programming type algorithms. But today we start talking about the model systems, right? So, model underactuated systems. So basically, if you look at the literature in the controls world and the robotics world on sort of the standard and novel control techniques for this type of robot, there's a handful of examples that everybody uses, right? There's a handful of examples that are well understood, I would say. Sometimes they're well understood that we don't have a good solution, but still, there's just a handful of examples. So some of them you'll have recognized, you recognize by name. Some of them we'll talk about today, but the Acrobat is certainly one we'll talk about today. Acrobat, not acrobat. Cart poles you've probably seen. But there's many actually. There's something called a Penjubot. There's a Faruda pendulum. Reaction wheel pendulum is similar. Something called a convey crane system. I want to sort of list some of them just so if you do know if you've seen this work, you'll connect the dots. The ball and beam is another classic one. There's a hovercraft model people talk about. And then there's this, what used to be called planar VTOL, that nowadays we should just call it a quadrotor, because that's what everybody likes, quadrotors, okay? So these are all sort of classical systems. They're all similar in the sense that they are just a few degrees of freedom, typically 2 degrees of freedom for many of the examples. And they typically don't have enough actuators. So they're underactuated in the trivial sense that you've got more degrees of freedom than you have actuators with which to control them. Okay, so yeah, there's a lot of great work, and one of the goals as we go through the different systems in the class is to understand what the world has done on these types of systems by showing some of the classic results from, let's say, nonlinear control for these systems and putting them in context. And then we're going to try to do, well, I don't want to say do better, but I guess that's what I mean. We're going to try to do better with sort of our algorithms, right? So we're going to see if we can have a generic solution that'll work for across the boards, because we're using things like value iteration and the extensions that are required to make them work for more complicated systems. Okay, so today we're going to bite off a few of them, the Acrobat and the cart pole, and then we won't actually spend too much time on the others because we'll try to. They'll mostly follow. They'll just be different instances of similar problems. But the Acrobat and cart pole are pretty representative. And then we'll play a little bit with quadrotors at the end, okay? Show you how it works. All right, so let's think about the Acrobat first. The Acrobat is a 2-link pendulum. It's an inertial pendulum now. It's not just a simple point mass model. So it's got theta 1 up here and theta 2 in the relative coordinates here. Okay, that's actually the way I've drawn it. That would be a negative theta. So theta 1 taking a negative value. Okay. It's got inertia in both of these links. It's got gravity pointing down, of course. What makes it special compared to sort of a canonical robotic arm is that we're going to give it a torque down here, and we're going to leave off the motor at the base. Okay? So just like it was actually Manolis who was just teaching in the room before us here. He's the one who made the joke before about if you had more research money, would you put more actuators on your robots? And no, we're going to leave that off for fun, not because we're poor. Okay, so the reason it's called maybe an acrobat is because it's sort of like an acrobat on a high bar, where you think that they do pretty amazing things, swinging around. They can swing up, they can balance, they can do flips, all the acrobatics. Okay, but they don't really have much torque to give at the wrist. They're going to do most of the work they're doing by a torque down at the waist. Okay, so that's in that sense you could think of it as a gymnast or an acrobat on a bar, but it's a robot, so we're going to call it acrobat. Okay, so the acrobat is going to fall neatly into our equations, our classical equations for the class, right? So we'll be able to write down the equations of motion with the manipulator equations. Okay, so in this case, Q is going to be just theta 1, theta 2. Okay, and B is going to be, it turns out it's going to be 0 and then 1. We don't have a direct control of theta 2 double dot, but we do have, we don't have direct control of theta 1 double dot, we do have direct control. So it's going to be 0 and 1 because U is just a scalar. Okay. Now H, C, and G can be derived very simply with the Lagrangian. I do it in the notes just for completeness, but these days you don't have to, right? So right, you can just count on them being implemented this semester by there's an Acrobat class, and there's a version that writes out the dynamics in H, C, and G form. If you want to think about it that way, there's also one that just pulls from the high-level robot description format. Okay, and what we're going to try to do with this is the classical problem for the Acrobat is to start from the bottom and swing up and balance at the top, right? Sort of surprising, actually, that when you're missing a motor at the shoulder, if you will, or at the wrist, if you're thinking of it as a gymnast, that you could actually balance it at the top, but it turns out you can. That's going to work just fine. There it goes, yeah. That's a randomly generated result. Normally it looks better, but what can you do? Okay, so, and if you want to see sort of the real thing, this is one that Ani did, your TA Ani. Let me see if I can get it to play from the start. Here we go. That's in lab. There's a little bit of a slop at the top that makes it hard to regulate perfectly, but it's perfectly, you can go up and knock it and it's balancing at the top. Yep, so that's in lab, right next to our couch and things like that. Okay. So the Acrobat's going to be the first system that we're going to take to fruition here. We'll do right alongside that, we'll do the cart pole. Okay, so the cart pole system, some people call it the inverted pendulum, but since we just did a chapter on the inverted pendulum, I got to call this one something different, right? So this one is you might have guessed it, a cart with some wheels on it on the ground, and then it's got an inverted pendulum attached to it. Okay, and it could be a simple pendulum, that's okay. which has got a mass here. There's some mass of the cart. Okay, there's some length here. There's an angle of the pole, and there's an x position of the cart. And we're going to apply, the control input is going to be a force on the cart. So again, that's going to fit into our manipulator equations. This time we're going to use the degrees of freedom as the x position of the cart, and then the angle of the pendulum. Okay? And our control input u is going to be this external force on the cart. So B in this case is going to directly control the first degree of freedom and only indirectly control the second. In both cases, if we want to make it interesting, we can add a torque limit. Okay, so again, this one is a simple system to play with. All right, so if you just drop it from a random initial condition, you can see that this is that was passive, so the torque was 0, and you can see, of course, there's an inertial coupling between the moving pendulum and the cart, and we're going to exploit that in the other direction in order to move the cart in order to swing the pendulum. Okay, and our goal is to swing this one up 2 to the top. And then you have to not only regulate the angle of the pendulum, but you'd also like to get the cart back to 0. Okay? And if you want to see this one in real life, if you make it, you could also make this one a little more interesting by, if you actually implement it, you probably have a finite track that you've implemented your cart on, so you have to worry about the sort of hard limits in x as well as in u. Okay? But this is an example of the cart pole swinging up and balancing. This is Philip Reist's work. Okay, and this one is just, this video happens to be showing that it's a very robust policy that gets back very quickly from every initial condition. Yeah? Okay, so all right, so that gives you a sense. So now the question is, how are we going to go about building the controllers for these systems? These are canonical underactuated systems. The rest of the ones, the Faruda pendulum, similar. You know, they're all of the same ilk. Okay, so the first natural question is, does the dynamic programming algorithm we gave you last time work for this complexity? And the answer is, yeah, yes, kind of, right? So if you're willing to discretize the 4-dimensional state space now, right? Then, so let's see. So for my pendulum implementation that I showed you, we had 51 mesh points per dimension. And not to say I might have been able to get that down a little bit, but so if I went to do this on the cart pole with the same resolution, I've got 51 to the 4th mesh points. That means I've got, I don't know, 7 million or something, you know, 7 million mesh points. My transition matrix, although it's very, very sparse, is the square of that. It starts to be something that I don't really want to, it just doesn't feel like you should have to throw the book, you know, like the power of distributed computation and the like at this canonical sort of simple underactuated system. So we're gonna say that the DP solutions are viable just barely for this, and really the best I've ever seen. I mean, because it's called the curse of dimensionality, right? That the amount you'd have to mesh goes up with to the power of the number of states, right? really, the very highest power solutions you see now in the world are 4-state, 5-state systems. You really, you're not going to see people doing value iteration for more dimensions than that, and that's not going to suddenly get better thanks to Moore's law. There's an exponential here that we'd have to wait some time before we can do 6 states, right? So and then if you want to do a humanoid robot with 68 states, you're out of luck probably. Okay, so so the discretized version of DP is, we're going to say, just borderline viable, but we're going to try to do better. We're going to try to find a more elegant solution. Now, we started last time talking about the continuous version of DP, and there's some hope there. We're going to extract some ideas there to get a pretty satisfying solution by the end of the lecture today for at least part of the problem here on the carpool and the acrobat. Okay, so there's a couple ideas that I want to pull out, right? So really the problem with this is that if we're discretizing based on these local function approximations, right? These sort of local cells that we've made some dense mesh over the state space, that's fundamentally going to break in high dimensions. That's just a no-go idea for high dimensions. You can't do that. So what can we do that's sort of a smarter representation over state for more complicated systems? Okay, so we talked about possibly using other basis functions. We're going to talk maybe a little bit more about that next week, but you could use polynomial basis functions or not. There's some limits into the guarantees you can get. There's a different idea that we can exploit here, which is trying to, instead of sort of making smarter basis functions directly, the first thing we can try to do is make approximations of the dynamics of the system, right? So maybe if we can say that, oh, well, in this regime, the system looks simpler, and I could use some very simple basis functions up here. Like if I'm close to the top, maybe I can say the system looks almost linear, right? And in the case of linear systems with quadratic costs, that was close to this case we did last time, we are going to have not only an efficient algorithm, but a closed form, so almost closed form, a closed form numerical expression for the dynamic programming solution at the top. Okay, and then the game after that is going to be, if I can do it sort of in the vicinity of the upright, can I do it in more places and sort of put together these smarter basis functions to fill the space? So I want to walk that path. I want to start walking that path with you today. So let's think about what it would take to linearize the dynamics around the top and how faithfully that will be able to capture the nonlinear dynamics. Okay? All right, so let's just talk a little bit about what it means to linearize and sort of to what extent it's going to capture the nonlinear dynamics, right? So linearization. All right, so the start here is that we've got some nonlinear dynamical system, f of xu, right? And what my goal in the linearization is to approximate this as a simpler system in the vicinity of some operating point. So I'm going to linearize about some place in the state and action space. Let's call it x naught, u naught. Okay? And linearization is trivial. It's just we're going to do a Taylor expansion of this function f to first order, right? So the way you've done Taylor expansions before, I'm going to say x dot is just, well, it's my function evaluated at that operating point plus the derivative of that function, the partial derivative of that function, also evaluated at the operating point. And the same thing in the other coordinate. Okay, and these things all, I mean, I can write out partial f, partial x, and everything. We're gonna give these things simpler names because they're familiar and everything. This thing, what is that? That's just x dot evaluated at the operating point, so we'll call that x dot naught, right? That's the derivative at the time derivative at the value at the operating point. This thing you'll recognize if you've done linear systems, state space form, that's just our A matrix. And this thing is our B matrix. So what I found, if I just take this first order Taylor approximation, is I can write the system as x dot minus x dot 0 equals A x minus x 0 plus B u minus u 0. And if I change my coordinate frame to be around in the vicinity of that point, so I'll define x bar to be just the relative to that operating point, and same thing for u, then x bar dot, of course, is just that. Well, then I can write this same equation as x bar dot is A x bar plus B u bar, right? So my goal was to take my original nonlinear system and get it into a linear system form, and this is a state space form for a linear system, right? This is a state space nonlinear equation. Okay, so the mechanics, that's probably familiar, but the mechanics are very simple for taking some function f, even if it's got h inverse, even if it's got b, all these things in there. It's just a matter of taking a few gradients and you can come up with a linear approximation of the system. And the big question I want to ask is that a faithful representation of the nonlinear system? To what extent? Of course, it's not going to be a perfect representation. To what extent is that a faithful representation of the nonlinear system? And what utilities are going to have in nonlinear control design, right? So, since we know what the phase portraits of the pendulum are, let's think about what the phase portrait of the linearization of the pendulum is. So, if I start with my pendulum equations, right, and I can write this in my state space form. These are all in the notes if you don't want to write it down as you go, but if I'm just going to write my f of x u, the first one, theta, the time derivative of theta is just theta dot. I have that on my state, no problem. Time derivative of theta dot is theta double dot, so that's easy to solve for. ml squared times tau minus b theta dot minus mgl sine theta. Right? That's just f of x u, right? For the simple pendulum. So we're going to linearize it around the upright configuration, right? So here, x naught is going to be pi 0. And then we'll linearize it around the 0 torque. So u naught will just be 0. And here, it's useful if you haven't seen this a lot, just to make sure we've done this once. Right, so my partial f, partial x, just to be clear, that f is a vector equation, x is a vector, so my notation always, and the standard notation would be that this element is f1. This is partial f1, partial x2. This is partial f2, partial x1, like that. Right, so the partial derivative always goes this way. I've got a vector equation. I add the denominator comes out this way. Yeah. So what's it going to be for this system? F1 is this. Partial of this with respect to theta is 0. Partial of this with respect to theta dot is 1. Now this guy, take the partial derivative of that with respect to theta. I get the m and the l cancel. I get a negative g over l cos theta. And then this guy is negative b over ml squared. Yeah? And I'm going to evaluate this at, well, at theta equals pi is what matters, right? So cos theta equals negative 1. So I get out 0, 1 g over L negative b over ml squared. Okay, that's my linearization. And then b is just, by the same mechanics, 0 over 1 ml squared. I want you guys to make sure you're comfortable with that, but I don't want, I mean, that's just manipulating some equations, no big deal, okay? But now I want to think about this for a minute here. Let's think about what this looks like. So let's actually replace it with some numbers here. So let's say mass equals 1, length equals 1. I can't quite make gravity equal 1, but I'll make gravity equal 10. We'll do the undamped case. Then I get 0, 1, 10. That's a 10. Zero. Looks like nice, easy numbers, yeah? Okay, so A and B are trivial here now. And if you remember, if you've had a class on linear dynamical systems, then we can understand everything about this in the same, using the same pictures we used to understand the nonlinear systems in lecture 2, right? So let's just think about how we do that. So the standard thing to do with a linear system is the eigenmodal analysis, right? So an eigenanalysis. And those of you that I've seen from 6003 know this well. Okay, so the best way to understand how this behaves in state space, our goal here is to cartoon the dynamics of this in state space, which is, you could think of it as x1, x2, or theta versus theta dot, right? I want to understand the dynamics. I want to draw the vector field in state space. My claim is the best way to do that is by looking at the eigenvectors of A. Let's go ahead and set u equals 0 first. Just like we did for the nonlinear systems, we're going to understand the passive case. So x dot just equals ax. And let's look at the eigenvalues of A. So, you guys all know how to do that. Let me just do it quickly. The eigenvalues are the ones that if I multiply A times the vector, I get a scalar back out. I'll take the determinant of that. And I'll find out that the eigenvalues of this thing are plus or minus square root of 10. And the corresponding eigenvectors, so if lambda 1 is square root of 10, then v1 is yes, and lambda 2 being negative square root of 10, I get V2 is negative 1 square root of 10. Okay, that's just the eigenvector and eigenvalue pairs for this matrix A, which you can get by just calling out eigenMATLAB if you prefer. Okay. Let's draw them on the phase portrait because it's very important. They tell me everything about the behavior of the system. So this is some vector that's, elongated like this. It's something like that. And this is some similarly elongated but in the other direction vector. They both should point through the origin. If I've got it right, okay. And the key, the reason to do the eigenvector analysis is because I can write down, if I write down x is some initial, if I have some initial condition x on V1, this one's V2, right? If it's just some place along this V1 axis, right? So if I've got some point here, then on this axis, the vector field is easy to understand, right? It's just x dot at that point is a times this, which is just going to be lambda times that. And since lambda here is positive, that's going to be, that means it's going to move along that same eigenvector, and since it's positive, it's moving away from the origin. Okay, similarly, if I have a point here, x dot is the vector is pointing away. It's along V1 pointing away. Right? Have you guys seen this before, these phase portraits for linear systems? Yeah, okay. And the same thing for if I look at the decomposition in the other eigenvector, I get a negative value here. So these guys are moving towards the origin. So along those eigenvectors, the dynamics are trivial. And then, of course, the additional step in eigenanalysis is that, especially in this case, since I'm lucky enough to have all of my eigenvectors being linearly independent, I can write any state x as a combination alpha 1 times v1 plus alpha 2 times v2. And my derivative is always just a linear combination of these simple responses. So basically, if I'm over here, then the response is a linear combination of this response plus this response put together. And so I get a vector diagram that's very easy to understand. It looks like this. This one's a linear combination like this. This one, right? So the linear system is easy to understand in the same phase diagram sense that we did before. And it's of course, we know that this was a linearization along the top. We know it's unstable, right? The points here are going to diverge from the origin. All right, so now the question is, to what extent is that capturing the nonlinear dynamics, right? And it's actually awesome, right? It's beautiful. So if you remember, of course, the eyeball, right? The pendulum eyeball, we had these sort of orbits of the nonlinear system that look like this, and then this eye of Sauron looking thing over here, yeah? Right, and another fixed point over here. Theta 1 versus theta 2, right? And then we had trajectories that look like this, trajectories that look like this, right? Okay, so we just took a linearization here around this point, and the thing we got back, it's too bad my art isn't a little better, was these eigenvectors with dynamics that looked like this, right? And local approximations that said the dynamics did this, did this, did this, and did this, yes? And it's actually a beautiful, very accurate description of the dynamics of this pendulum in the vicinity of that fixed point, of course, and it's, I think that's a pretty reasonable way to think about the pendulum. Maybe, I don't know, here, something like that. I don't know. At some point, it's really bad, right? But there's a big part of the state space where that's actually a pretty good description of the dynamics of the system, right? So, at the beginning, I tried to say feedback linearization is bad. I'm sort of against feedback linearization. If I have to take a stand, if I have to be, so feedback linearization is bad. But there's nothing wrong with linear systems. Linear systems are beautiful and good, right? I like linear systems, and you can solve them, and it's great. The only thing is you shouldn't turn your nonlinear system into a linear system by brute force. It's that brute force part that I don't like. But if you have a linear system, they're rich, they're beautiful, they're good, right? Okay, so linearization is a perfectly viable way to try to make good approximations of the nonlinear dynamics. And you could imagine, as we'll go on in the class, maybe if I could make one approximation here, another approximation here, maybe some approximations somewhere else, then maybe this is a nice way to get an understanding of the whole system with better basis functions than, let's say, some simple meshes with triangle basis functions, right? Okay, so let's just worry about this area for now, but that's a big idea that we're gonna get back to. Okay, so all right, so that was just the passive dynamics, right? If we want to do control design, we care about the control input. So we have to think about the rest of the case, right? So again, the eigenmodal analysis is sort of is a good way to think about it, right? So if I can write any vector x as some linear combination of the eigenvectors, right? These are and just some linear combination of it with some vector alpha, right? If I can write any vector like this, then I can think about the dynamics in this. The reason to think about the dynamics in that space is because on those vectors the dynamics are trivial. Okay, so if I want to write down x dot equals ax plus bu again, right? And if I were to now change coordinates to this alpha space, that's just, I've got orthogonal, linearly independent vectors, so I could just rewrite my dynamics in the coordinate system of those vectors, right? So that would just be, that because these are linearly independent, I can take an inverse, right? I can just change coordinates between x and alpha easily. Right, so then I can write down, if I just pre-multiply everything here by V inverse, and then change my coordinates internally here, I get and the magic of doing that, of course, is that this thing it becomes a diagonal matrix. That's what we just saw. By virtue of that being an eigenvector decomposition, I see that alpha 1 evolves completely independently from the rest, right? Plus the sort of the ith row of this V inverse thing. Okay, so the question you should have in your mind when you think about, do I have sufficient control to change that vector field, since the dynamics are sort of independent along the different eigenvectors, The question is, can my control affect the dynamics on all of those eigenvectors? Right? That's a yes or no answer. Either this thing has enough elements for me to control, to change the dynamics on every one of those vectors, or it doesn't. Okay? And that, just checking that this thing is sort of non-zero in the right way, is the question of controllability. In checking that this is non-zero is a simple thing to do when you're lucky enough to have linearly independent eigenvectors. But in general, there's a controllability Gramian that you can that's sort of the formal way to check controllability of a system. You can, maybe I'll skip the details, but basically you can ask a question for any linear system, A and B. Is it controllable? Yes or no, right? And, this is shameful, but you can just call controllability in MATLAB, give it A and B, right? And you just want the rank of this controllability Gramian to be, the full check is, you check the rank of that has got to be equal to n, okay? But there's this notion of can I control every aspect of the dynamics with my linear system? And this is a classical linear systems thing, but we're not going to use too much, except to say I wanted to point it out since we had all the pictures up available in thinking about eigenmodal analysis. I wanted to bring this up because controllability asks the question, can I take under control, do I have enough control authority to drive the system to the origin from any initial condition? That's the question of controllability. And you might think that an underactuated system is an uncontrollable system, but you would be wrong. Right? In fact, we're going to see again and again here that the Acrobat, for instance, trivially underactuated, okay, is perfectly, the linearization at the upright is perfectly controllable. You do have enough control authority to drive the system back to the origin, even if it gets knocked away. But it requires an interaction of the different degrees of freedom to get there. You don't have instantaneous control back, but you can find a path back. Okay? And the beautiful thing is, for linear systems, asking whether you have that property is a simple yes or no answer that can be given just by from A and B. Okay? So controllability does not equal underactuated. Oh, that should be. Certainly you can have underactuated systems that are uncontrollable. If I have no motors, then I might be up a creek, yeah?
If A is not PSD, does that mean the system is just not linearizable at that state?
Right, so there's a question of if you have zero eigenvalues in A, then it can be that there's a deeper question there that we're not quite getting to, but there's a question of how informative the linear system is about the nonlinear dynamics. And in the case where you get zero eigenvalues of A, then it's basically the stability of the linear system does not imply anything about the stability of the nonlinear system. I think that's what you're asking, right? So there's a degenerate case where if you come back and you get some zeros in the eigenvalues of A, which would be neutrally stable, right? The nonlinear system could actually be stable, or it could actually be unstable. You can't tell because the linearization happened to go to zero around there. Yeah? Okay. All right, so let's do feedback design for the linear system. So there's lots of good ways to do feedback design for the linear systems. If we're willing to linearize and say that's a pretty good description of the dynamics in some vicinity, then maybe we can take those linearizations and do linear control theory, which is very advanced. That's sort of, that's the message coming in, is that linear control theory is very advanced. nonlinear control theory, we're working on it, right? So, so lots of good ways to do linear feedback design. Now we're going to do it as a dynamic programming problem, right? Just to make a contrast, let's, remind you what it would be like to do it without optimization, right? So, let's say I was doing classical control design for a linear system. If I've got my linear system AX bar plus B U bar, and let's say I'm going to design a linear controller because I want everything to be linear. I'll say negative K1 theta minus theta naught minus K2 theta dot minus theta naught dot. That would be sort of a PD controller. If I wanted to put a PD controller on the gains here, right, which I could write that as just negative KX, yeah, bar. So a classic approach to doing this would be, let's say, this is a multi-input, multi-output system, but you could do pole placement approaches to this, right? So I could write this as a closed loop system, X bar equals A now minus BK, X, right? And I could look at the eigenvalues of this, for instance, and ask, what happens as I change K? Can I move the eigenvalues to something that I'm happy with? I guess I'll just admit this is my straw man. Straw man is pole placement, right? Which is a very popular approach to control design in the industrial world, and in people have been doing it for years and years. Okay. Now, the challenge that I want to point out here is that actually, if I choose K wrong here, it's actually, there's a couple, every time I choose K, if I move K1, then the stability is going to change, and it's hard to tune both K1 and K2 by hand at the same time. For the simple case of PD control, people have relatively good techniques, but it's hard in general, right? And if you look at, just for the pendulum, let's say, and you look at just which values of K1 and K2 give me stabilizing controllers, I did it for us here. It's K2 has got to be greater than 2 square root of K1 minus 10, and K1 has to be greater than 10, which is, that one's actually, that's MGL. That one's sort of reasonable. Okay. But there's some values of K1 and K2 that'll give me even a stable response. Okay, but I have to be artful in choosing them. What we're going to get today instead is by formulating an optimization problem, saying I'd like the response to be optimal by some metric, is that you might complain that you have to choose the cost function. I have to choose my weights. But for any choice of weights you make, or for trivial choices of weights, as long as you say positive weights, for instance, you're going to get a stable controller out, right? And it just makes it's a just much nicer design space to work in, right? For any objective function I give, I'll get a stabilizing controller, and really I've changed the game from finding a stable controller to really highlighting I'm going to shape the controller to the one I want, right? So the difference between choosing the gains directly, I'm contrasting choosing the gains directly with choosing the cost function and then solving an optimal control problem. And I strongly favor choosing the cost function, right? For free, or just a little bit of elbow grease here. All right. So let's put DP to work for the linear systems and make sure you've seen that result, okay? Does that make sense? I mean, how many people I don't know if I just made it bad to do this. How many people have sort of used pole placement to design a nonlinear system or a linear system? Sure, right? I didn't mean to say you're bad. I'm just saying that, your life could be easier, right? I hope, So that's a powerful set of tools, but we've got better tools. Okay, so let's remember the big message last time. And by the way, I felt like I crammed too much in the lecture last time. And on the way home, I thought a lot about it, and I actually rewrote the notes completely in a totally different delivery. Okay, it took me forever. Okay, so I could ask you to read it and tell me if that worked better for you, but you're tainted because you've seen it once. So of course, the second time you'll see it, you'll think it makes more sense. But do read it, and see if maybe that'll clear things up or whatever. And just because I worked hard on it, and I'd like you to read it. So the notes that are posted for the second part of dynamic programming, are a different presentation of that. Well, see the same equations, but in a different sort of simpler order. Okay, and removing some of the details that I shouldn't have shoved at you. So thank you for your, feedback, even if it was, kind of a I don't like you right now feedback, right? Always trying to make it better. Okay, so one of the big result from last time that I wanted you to remember really was that we could think of the value iteration update as a sufficiency condition. If I can find a j that matches where the value iteration update does nothing, then that's actually more than just an algorithm. That's a certificate that the system is optimal, that I found an optimal controller. And that there was a sufficiency theorem that was supposed to close that, and it got worse. Okay, and the big takeaway from last time was that there is a sufficiency theorem for the continuous systems, which looked like this, the Hamilton-Bellman-Jacobi equation. Okay, which this also has a sufficiency theorem, right? The Hamilton-Jacobi-Bellman sufficiency theorem. And it requires things like J, the derivative, to exist everywhere. There's a few other assumptions which I list carefully in the notes about continuity of solutions and things like this. You can't have some of the most bizarre things that nonlinear systems can do, but for well-behaved nonlinear systems, this is a sufficient, if I can find a j which satisfies this equation, this is a sufficient condition for optimality. Okay, and then we looked at a couple cases where we could actually make this even easier by getting rid of that min over u, because we could solve for u exactly. And we're going to do that again now. But let's just take a minute, in case it didn't come across last time, to marvel at how nice this result is. Okay, so we're talking about understanding the infinite horizon behavior of a cost function for a complex nonlinear dynamical system. These things, I'm asking you about the performance of a system if I were to integrate the equations of motion through whatever they're going to do, evaluate a cost along this integral till time goes to infinity, which is hard to do numerically, yeah. And somehow I'm not just going to ask you for one trajectory, I'm going to ask you for all the trajectories, right? And I want to ask you just not about what the cost is, is it optimal? Right? That's a really, really hard set of questions to ask. And to somehow be able to check that with a point-wise, there's no integration in here. If I just say for all x, this condition is held, then I've somehow proven this really, really hard thing about the whole long-term behavior of the system, right? So that's really big time result, okay? And that's really a go-ahead enabling idea for why optimal control works so well and why additive cost is such an important way to write down optimal control problems. Okay, so in the special case of this being quadratic in U and this being affine in U, things got a lot easier, right? So that's certainly the case if I start off with ax plus bu, right? And if my cost is like this, okay? I'm affine in U, and I'm quadratic in U here. And this is the very famous problem, which you might have you might have derived it before, you might have even used it on your robots before. This is the linear quadratic regulator problem. Also known as LQR. Okay, so I'm going to regulate my linear system to the origin. My goal is to make the origin, all trajectories go to the origin because I'm penalizing the distance from the origin here. And I want to put a quadratic cost on being away from the origin and on control input. Okay, now to be clear here, I'm going to make some extra requirements to make the math work. That Q is a symmetric matrix that is positive semi-definite. Its eigenvalue should be 0 or greater. And R, even a little more restrictive, R should actually be positive definite matrix, because we're going to take an R inverse. Yeah? Okay, so in this particular case, this equation becomes very manageable. Still a little gross, but manageable enough that we can solve it. Okay, so there's a magic step, and it's annoying maybe, but there's a magic step, which is that someone smarter than us is going to tell us that the solution of this thing is always going to be some quadratic form. The cost to go is going to be some quadratic form. Okay, so this is sort of given. All right. Someone figured out that if you just guess J is going to have this form, now the values of S are to be solved for, okay? But we're going to restrict it to be quadratic in S with a positive definite form, okay? Then we're going to be able to solve this equation and prove that there is an S here that is optimal. The cost to go is quadratic. Okay, so I'll cartoon the steps here. The full derivation's in the notes and is not too bad. Right, so partial J, partial X here is 2X transpose S. You gotta get used to the matrix derivatives. It takes some time, but it's worth it. Okay, and then so I could write this whole thing out as 0 equals min over U, X transpose QX, U transpose RU plus 2X transpose S AX plus BU. Okay, and if we look at it again and just look at its structure here, it's quadratic. This whole thing is, this whole term here in the brackets is a quadratic function in U. Use a vector now, but still, it's just a quadratic function in U. R is positive, so it's actually a nice convex bowl in U. So I can find the minimizing U by taking the partial derivative and setting that equal to 0. And I get something that is very similar to what we saw before. It's negative R inverse B transpose S X. Okay, that's the minimizing value of U. And now this, so when you see Sx, you should be thinking partial J, partial X, right? This is really the same story I told you before, right? So XX is the same as partial J, partial X here. Modulo transpose here, I'm missing a transpose somewhere, but this is, yeah, that's the, yeah, okay. And a factor of 2, but, right, this is the same story I told you before, that if I have a nice quadratic cost to go function now, right? J is some quadratic bowl. The optimal control is go downhill as much as possible, modulated by B, because I can't necessarily go straight downhill. If I've got B has got some 0 elements, I'm going to have to go as downhill as I can, given my control inputs. And then, okay, maybe I favor some control over some other control, so I'm going to I'm going to modulate that by R inverse too, right? But this is really go downhill on that quadratic bowl. That's what you should see when you see that. Okay, and if you pop that back in, you'll get something. You see there's an x. This is also, the other thing to note about this is that it's linear in x. I can just write that as negative kx. So linear feedback is optimal for this cost function. That's good. That's good news. It makes our life better. And if I stick it back in here, you'll see everywhere I've got a u, I get an x there instead. I get a whole big expression which is quadratic in x. And it has to be true, it has to be equal to 0 everywhere. So I just get, what I end up is a matrix equation in this, right? So I get a big expression which says 0 equals x transpose something big x. That has to be, for all x, this has to be equal to 0. So it's going to be sufficient to say that this thing has to be equal to 0. And that thing turns out to be some pretty scary looking, but it could be worse, I guess, but some very famous equation. This is a Riccati equation. Matrix Riccati equation. Algebraic Riccati equation. Okay. So now our task is to solve for S. That's tough looking at it, but it turns out there's well-known numerical techniques for doing it. If you know these things, you use a Schur complement typically. Okay. And the punchline is that there's well-known recipes for this. You can call the algebraic Riccati equation solutions in MATLAB, or you can even just directly in MATLAB call LQR, and what you get out is K and S given LQR. You just tell it A, B, Q, and R. Okay? I find myself making this sort of very scary measure of importance. Like obviously it's an important result if there's a MATLAB function that has the name, so by the MATLAB test, it's important result, right? Okay, so in practice we can really just call, if we can find the linearization of a system, we can get back a linear feedback controller and the cost to go function, and we've done continuous dynamic programming exactly, and it'll be good for sort of the big region of state space that we care about, but not the whole system, right? Okay, so these days the tools are pretty good. If you give me a robot, like the ones I was simulating in MATLAB, we can just call linearize. We can call you give me the system, you give me Q and R, I'll give you back a controller that does the linearization about it, right? You'll see that in the code and you'll be able to work with it. What's impressive is that this is going to work surprisingly well. So the solution of this S is numerically very efficient. You can do it for even very big systems. Okay, so we're not plagued to the curse of dimensionality the way we were with the grid-based methods. I could solve a 100-dimensional system if I wanted with this. Okay, certainly we can solve our 4-dimensional systems with this. And it's going to give me a controller if you pick a Q and R that are positive, as long as the system is controllable. If A and B define a controllable set of linear systems, or a linear system that's controllable, then it will give me back a K and an S where K stabilizes the system, right? As opposed to pole placement where some of the K's worked, some of them didn't. Any values of Q and R that satisfy just this check will give me a stabilizing controller. And what's more, the stabilizing controller is actually going to be, you'll be able to sort of shape the features of that stabilizing controller given these Q and R. So if I care more about getting there fast, then Q being bigger than R is what I want, right? If I want If I want to get there eventually, but I really don't want to use much control effort, then I make R big, right? If I care about x1 more than I care about x2, then I can shape the elements of Q appropriately, okay? All right, so let's just see that in action here. So literally in the code we've given you, you can just call LQR. This is the time invariant LQR, because we do have a time varying case that we'll talk about later. I just give it the system, the cart pole plant. I give it my X0, my U0, Q and R. It'll give me back a controller in this case, okay? And if I just run LQR on this thing, and by the way, that call will fail if the system is not controllable, but the Acrobat and the cart pole are both controllable even though they're underactuated, and it stabilizes the cart from a range of initial conditions. Now I've tried to pick a range of initial conditions so that with some small probability it'll fail. The cart pole is kind of fun. If it does fail, it'll just race off to the side and just disappear like it. Okay. Same thing for the Acrobat. Started from, see, that was too much initial conditions. It was outside the region where the linearization worked, but actually pretty big perturbations if you bang on the Acrobat, and it's again only applying a torque at the elbow, but it's using the inertial coupling between those 2 degrees of freedom to stabilize the origin at the top. Yeah?
So what prevents you from just having different linearizations for different parts of the system and trying to just mesh them all together?
That's what we're going to try to do. And that's why there's a TV LQR, because the problem is that if I pick a linearization over here, it's not a fixed point of the system, so it's not a linear dynamics, it's an affine dynamics. The system, even with 0, is going to move around. So we have to do something a little smarter, but that's where we're going to get to. Yeah?
But if you handle some part of search space where AD is not controllable.
So your goal, the place you need to stabilize should be controllable, right? So if it's not, you got to add a motor. You got to get the extra research funding, yeah? Because there's nothing you can do about it. But you can actually pass through regions of space that are uncontrollable. And if you affect some, so for instance, when I'm running, right? Once I leave the ground, there's nothing I can do to affect the trajectory of my center of mass. That is an uncontrollable system, right? But I can still get to the desired place in space by using the opportunity when I'm on the ground to control and regulate, and then just being unstable for a short time. And so for over the course of a trajectory, if you pass through uncontrollable regions of space, you can still potentially achieve your goal at the end. Yeah?
It seems, so the result that we got seems to indicate that the controller is linear, like a linear function x. So doesn't that mean that it does correspond to like placing certain poles down?
It absolutely does. I'm just saying, okay, that would be another thing to say. Is we're doing pole placement too, but instead of choosing K1 and K2 directly, we're going to choose Q and R because it's an easier way to choose those same gains. That's a more friendly way to say it, I guess. Yeah?
Is controllability a measure of how well the linearization matches?
No. The controllability is only so the tools for controllability only work for linear systems. They know nothing about the nonlinear system.
Okay. And how do you know when the linear model or the linear approximation stops?
We're going to give you a very good answer to that, but it's going to take a little work because you have to use convex optimization and bring some tools down. But actually, that's a perfect point. So yeah, so if we are going to tile the space with sort of controllers that are good, one of the things that we need to know is when that linear controller stops being useful for the nonlinear system. And it turns out that's a problem we can solve with nicely with some good tools. We'll be able to find regions where I can guarantee the linear system is going to work. Yeah.
And we have actuation limits in this framework?
good. The LQR does not have actuation limits, but on Tuesday we're going to show you the way we do that in practice, right? So just to give you a hint for it, so basically what we'll do is we'll solve the Riccati equation, the LQR problem, as if there was no actuator limits. And then when we actually go to try to go downhill, we'll take into account the actuator limits, right? So we'll go downhill as best as we can given the actuator limits, but still pretend that after that I would have had infinite, or whatever torque I needed. And that turns out to be a powerful thing that we can do even on humanoids, for instance, okay? All right, so there's a couple more things to say here. So let's think about quadrotors for a second, okay? I'm trying to decide if I should try to draw a quadrotor. I probably shouldn't. Yeah, you know what a quadrotor looks like. It's not going to look good, right? So I'll just not draw it, okay? But I can write the state space, yeah? So for the quadrotor, let's say there's a first version here, which would be the planar quadrotor, where I have just the quadrotor constrained to a plane, where I have the coordinates are now the x and y positions, let's say, plus the angle of the quadrotor, right? Oh crap, I'll just draw a quadrotor. All right, so, oh, look at that. That's not so bad. Yeah, so that's my xy position, and then I call this theta, let's say. Okay, and then my control inputs u here in the planar case are just thrust here, like force 1 and force 2. So I guess a planar quadrotor's really only got 2 rotors. Maybe it's a birotor, but we'll call it a quadrotor because it's the cool thing these days. Okay, so u is just f1 and f2, right? So this system is now got 6 state variables, 3 degrees of freedom, 2 actuators. Probably those are going to be limited. You're going to have, these days they have pretty big motors on the props, but there's still torque limits. Okay, they're especially limited because you can't typically with your prop you can't suck on the air, right? You have a unidirectional thrust. Okay, so we can put this together. It's trivially underactuated because it's got 2 inputs and 3 degrees of freedom. Okay, but nevertheless, it's controllable about the origin. So you take a simple model of the quadrotor. You decide on what your relative importance are between q, y, or x, y, and theta, and your force input. You can call the linearization in MATLAB, and that's going to work just fine too. All right, so here's my little, actually my MATLAB animation is not much better than my hand drawing, sorry about that. But it's actually, this is why quadrotors are great, because even just the simple linear control here, you have so much control authority, you could stabilize almost anything just with linear control, yeah? This is sort of why, I think why they're so popular. Huge range of initial conditions will get you right back to the origin, okay? If you think about the 3D case, then the problem gets a lot more interesting because you have a choice here for how you're gonna write your state space. For now, let's just pretend let's just write it like x, y, z, and then roll, pitch, and yaw. And then my u is going to be my 4 rotors, my 4 propellers. Okay? Now why is that? Why do I say there's a choice to be made there? If you guys have thought about 3D rotations ever, roll, pitch, and yaw can potentially have singularities. So, so a controller designed on these coordinates would blow up if the quadrotor goes just to the wrong orientation, and that's no fun. So we'll typically do things, we'll work towards doing things in a quaternion coordinate frame here. But then LQR gets a little bit more ugly because you have constraints on state too. So let's just think of it like this for now, and put a note that caveat. There could be singularities in in the dynamics, written this way. Okay, and the other thing is that I wrote prop here instead of thrust, instead of force, because here when I write down the dynamics here in the full 3D case, I end up first of all with a B that's a function of Q. Okay, it's not just a static B, but I need to take into account both the thrust produced by the propeller, but also the moment produced by the propeller. If otherwise, it's actually not controllable in all 6 degrees of freedom, but it is controllable if the dynamics include the moment induced by the rotors. Okay. And now we've got a 6-dimensional system. I would say the mesh-based dynamic programming is not viable there. Okay, but the linearization for the quadrotor with big enough motors really works extremely well. If you're thinking about the torque limits a lot, and I said that these are, for instance, F1 and F2 can only be positive, you might think, oh, that's, I'm always I'm living right at the limits of my one of my torque limits, but in fact, I have to have non-zero F1 and F2 just to find my fixed point, right? Just to hold myself. So I'm linearizing around someplace in the middle of my torque space, hopefully, yeah. And sure enough, these things just work, right? So if I won't do that right now. So I'm actually simulating, when you guys see things like successive zero crossings, that's actually because I'm simulating with the torque limits, and the integration is being thoughtful about when you're hitting the control limits. So this one's probably flipping out actually. Maybe I'll choose less aggressive initial conditions next time, but. No, it's not. It's because I changed networks and my LCM traffic is not going across the new network. These are the pains of software. Okay, here we go. See? Apologies, Pat, for not using your better viewer. Next time. Okay, so quadrotors are easy if you're willing to linearize. And we're going to get to the point where we can do pretty fancy things with quadrotors. We'll get them darting through trees and forests and the like pretty soon. Okay. Good. The last thing, which I'll put in the notes and I won't bother writing out here, is that if you want to linearize a system based on the manipulator equations, the structure of the manipulator equations is actually very compatible with doing linearization. It's much, much easier than just if you had an arbitrary F and X grab bag. Okay, so if you find yourself with H, C, and G on a piece of paper and you want to find the linearization, then it's actually much, much easier than you think. So that'll be in the notes if you like. Okay, thanks very much.